Okay, here we go. A lot of information here, short amount of time. Some of it's repetitive or review, but try it again. So, what do we need to do to analyze a polynomial function that's of higher degree? I'm talking about anything that's bigger than like x squared, x to the third, x to the fourth, and so on. First of all, end behavior. If I have x approaches negative infinity and positive infinity, negative infinity is just talking about what's happening on the left side of the x-axis. Going to positive infinity would be on the right side of the axis. And you've got two options. Either your function is going to negative infinity, which means that it's going down, or positive infinity, which means that it's going up. Okay, your x-intercepts, we're talking about the roots, the solutions to the quadratic or the cubic or the quartic or whatever. Test values, those are just points that we're going to pick that are within the x-intercepts and at the ends of the x-intercepts to kind of get a better look at what the graph's going to look like. And then multiplicity is kind of talking about the curvature of the graph. So here we go. We got end behavior. The option, let's talk about even degrees first. And a positive leading coefficient, so like x to the second power. That's a parabola, so it's going up and up. So on the positive side of the x-axis, the function is going up, so to infinity. On the right side, the left side of the x-axis, or negative side of the x-axis, we're going to up again, so positive infinity. Now, if it's an even even degree and a negative leading coefficient, like a negative x, now let's say to the fourth power, it would have been going up and up, but what that negative is going to do in front is make it go down and down. So it's now negative infinity and negative infinity. Okay, when your degree is odd, like say x to the third power, it looks like this, down and up. So on the right side, the function was going up, so positive infinity. On the left side of the x-axis, the function is going down, so negative infinity. Okay, so I'll stick with that x to the third, but now I'm going to put a negative whatever, maybe a negative 4. That negative symbol is going to take what should have been up on the right and down the left. It's going to reflect it over the x-axis. So now we're going to negative infinity on the right and a positive infinity on the left. Now when deciding what your end behavior should be, what I do is I look for the exponent first, and then I look to the leading coefficient next. So cubic up on the right side, down on the left side, so that looks like it'd be letter A. Now, what's the other odd power up here? Looks like it's to the fifth power, but now it's a negative leading coefficient, so it's a reflection over the x-axis. So it looks at D. Okay, even power, okay, so fourth power, I know it's not the very first term, but fourth power is the biggest power. And a positive 1 out in front, so it's going to look like C, where it's going up in both sides. And then finally, 6 is the bigger than 5, so 6 is my degree. Leading coefficient of negative 1, it gets flipped over the x-axis, so that would be graph B. Okay, your x-intercept zeros, roots, or solutions, they're the same thing. They're just different ways of saying this. A polynomial might have multiple roots, like x to the fifth power has got 5 roots, but that doesn't necessarily mean that they're all x-intercepts. To find x-intercepts, I'm either going to factor it, do synthetic division, or maybe even the quadratic formula to find those answers. This first one, I noticed that they're all divisible by x, so I'm going to take that out. So I've got a greatest common factor of x, and I'm left with x to the fourth plus x to the second minus 6. One way to get x to the fourth would be x squared and x squared. A positive and a minus. What are the factors of negative 6 that add up to be a 1? I'm going to go with a positive 2 and a negative 3. And along with that x in the very beginning. I'll set each of these equal to 0. So one answer, x equals 0. The other answer, I'm going to subtract 2. Take the square root, and here I'm going to get complex numbers, so it's going to be an actual root, but it's not going to give me one of the x-intercepts. So I could say x is equal to a positive and a negative I squared root of 2. Okay, x squared, I'm going to add 3. Now I'm taking the square root of a positive number, so I get x is equal to a positive and a negative square root of 3. So 5 roots, but not 5 x-intercepts. Okay, polynomial, there's 1, 2, 3, 4 terms, so I'm going to factor by grouping. These two are both divisible by x squared. And I'm left with x plus 3. I need to factor something out of the next couple, the next pair, to get an x minus 3. So I'm going to take out a negative 4. They both have an x plus 3 in common, so there's one factor. And then they're left with x squared minus 4. I can factor x squared minus 4 a little bit farther if I want, but I can solve that by square root, and I get x is equal to a plus or minus 2. And here I could solve, and I could get x is equal to negative 3. So third power, I end up with 3 answers, so I end up with giving 3 roots. Okay, very similar up here. Just kind of keep through it. In fact, I'm going to skip these two just to cut it straight, but to start this one off with, I probably would just take a negative 2 just to save some time. Here, I would take out a greatest common factor of x and keep on factoring along the way. Now, multiplicity. I could have a single root, so like x minus 3, that's not going to show up very well. Let's go x minus 3, set that equal to 0. X is equal to just positive 3. I get one single spot where it crosses the x-axis. If I have, say, x minus 3 2 times, that means it's going to cross the x-axis actually at 3 once, but I'll end up giving this curve because of a double root. If I had x minus 3 to the third power, there's 3 of that root, so I get a triple root, which looks a lot like a single root, but a little bit more curvature to it. Okay, so I'm going to use those tips to find out what this graph kind of looks like. First, the end behavior. This is x to the first, x to the first, x to the first. It is a cubic, so third degree. So my end behavior should look up and down, but because of this negative 2, it's actually going to flip over, so it's going to go up on the left and down on the right. X-intercepts, I'm going to take all these, set them equal to 0, and solve. So one of them would be at 0, x-intercept. Another one's going to be at positive 3, and another one's going to be at negative 2. So in my label, or my xy table, or xf of x table, here's what I'm talking about with test values. Negative 2, 0, 0, 0, and 3, 0 are my roots. So I'm going to pick values of x to put into my equation that are on the outside of my root, so like negative 3. In between my two roots are my two x-intercepts, so I would pick like, say, like negative 1. Okay, or in between 0 and 1, put a 1 there and maybe a 4. What that's going to give me are just some numbers that tell us what's going on. Okay, here, because I just have one factor of x minus 3, I know it is a single root. This one is also a single root, and this is also a single root. So now when I cross at 2, it's going to be a straight line, straight line, straight line. My end behavior is up this way, down this way. Now, when I put in a negative 1, it works out to be a negative 8. And what I mean by put in, I mean if I put in negative 2, negative 1, negative 1, and negative 3, okay, negative 1 and a plus 2, it works out to be a negative 8. If I were to put in 1, it works out to be 12. So at 1, negative 8, something like here, something up here, and then that gives me a good idea of what that graph looks like. Okay, easy enough. Didn't even need a calculator to figure those out. Okay, so here, very similar. X to the first, x to the second, and then third. So really it's an x to the 6th power. So even, up, and up. Okay, now my roots, I could set this equal to 0, but that's not going to get me an answer out of it than the 0.25. But one would be at negative 5, negative 2, and 1. So again, make my table negative 5, 0. Maybe I put a negative 6 to get an idea of what it looks like. My other root, negative 2, so maybe put negative 3 in there to see what it looks like. 0, I'll put that in there because it's between negative 2 and 1. See what it looks like, and maybe put in a 2. Okay, so there's my test values. Multiplicity would be, because there is to the first power, this is going to give me a single root. Here, because it's 2 of them, it's going to be a double root. Because it's third power, it's going to be a triple root. So what that really does for me is I now know that at -5, it's going to kind of come here straight. At -2, it's either going to curve and hit it once there or like that. Okay. And then at 1, it's going to come through and it's going to be kind of squiggly. Okay. Now, how do I know where it's going to hit at? Well, I type in -6 and I should get some negative number, some positive number that's way up here because of my end behavior. If I were to put in 2, I should get some positive number that's way up here as well because of my end behavior. If I put -3 in for all these x's, it works out to be like -32. So -3 is somewhere way down here. So it's going to come back down. Okay, come up to -2 again because my double root, it's going to kind of curve and hit. So if I put in 0 for all of those x's and worked it out, I believe it works out to be -5. Oh, sorry for about the crazy zooming. So 1, 2, 3, 4, 5. Okay, it might come down a little bit, but it's going to come up here at 1 and give me that little curve action. And there you go. You got kind of an idea of what it looks like. Oh, and by the way, another key feature. This is also my y-intercept. Okay, now I know there's more examples in the notes, but again, I can go over those when we get back in class. But hopefully this is enough